Okay, so yesterday we had worked through that first example, and I asked you guys to take a look at example number 2. So let's do this real quick. All right. So it says a motorcyclist, I don't think I've ever used that word before, driving at 30 meters a second, presses the brake, slowing at 4 meters a second squared for 6 seconds. If he ends at a position of negative 50 meters, then make a position time and a velocity time graph. Okay, so this one's very similar to the one that we did yesterday. So you're going to kind of plow through it. The next example is the one that's got some sort of new stuff in it. All right, so let's see if we can identify what these numbers are. So 30 meters a second. Thoughts about what that is? Sure, what do you got, Michael?
Initial velocity.
Cool, that's your initial velocity. That's how fast he's going before he pushes the brakes, right? Okay. And then it says he's slowing at 4 meters per second squared, right? So that's going to be a measure of, sure, we got Alexander? Very good, that's the acceleration. How'd you know that was the acceleration? Good, because it's meters per second squared. Everybody good with that? Cool. Maddie, right? Why am I drawing a blank? Sorry. Maddie just said it should be negative. I was going to ask about that at the end. How do you know it's got to be negative? He's slowing down, and so, arguably more importantly, that means his velocity is decreasing. Okay? Now remember, you guys, negative acceleration means decreasing velocity. There's a question on the lab about that. All right? So make sure you guys get that. Negative velocity means, or negative acceleration means velocity is decreasing. All right, and then it says he's doing that for 6 seconds, so hopefully you're all able to identify that 6 seconds is the time. And then it says he ends at a position of negative 50 meters. So is that my final velocity, you guys?
Yeah, that's your position.
Good, that's my final position. All right, so that's the other thing that sort of comes up here now. So now, because we're talking about both position and velocity, you're going to have both initial and final velocity and initial and final position. All right, initial and final velocity are going to be VI and VF. Initial and final position are XI and XF. Cool? All right. Now, the next thing that we need to worry about is sort of what do we need to calculate? Well, to make my graph, I need to know, I think up here there's a total of 7 variables. There's these 4, and then a couple others. So the things I don't know, and I'm going to have to find in some fashion. I got to figure out what my VF is. I got to know what my displacement is, and I got to know what my initial position is. Those are the 3 values that I don't know. Everybody okay with that? All right, as a quick note, well, I'm getting ahead of myself. Okay, so everybody good? All right, so to find my final velocity, let's take a look at our toolbox up here. Anybody see an equation that we can use there to find the final velocity using the given information here?
Final velocity.
Yeah, so read it for me, Chris. What do you got?
I did 30 plus negative 4 times 6.
Yeah, so that's this guy. It's VI plus A times T, right? So again, I'm just going to, you guys can all plug in the numbers. Please make sure you remember to make that acceleration negative. This negative sign is kind of hiding here still. I need to calibrate my board. So you end up getting 30 minus 24, so you end up getting 6 meters a second for your final velocity, right?
Yes.
Everybody good with that? Okay. All right, so everybody good with how we found the VF? Okay, now I got to find my displacement. So to find the displacement, you can use any of the options, right? Because I know VI, VF, A, and T. So you can use either the screwdriver, the drill, or the vice grip. They all work. Again, I think a lot of you guys seem to like using the screwdriver one, so we'll go with that. It's 1/2 VF plus VI times the time. So is that right? Let's see. 36 divided by 2 is 18 times 6. What's 18 times 6? 72.
Wait, how do
Am I doing that right? Yeah, I don't think it's 108.
No,
There, 18. times 6. Oh, 108. It is. My bad. Sorry. I have that written down somewhere. I should have pulled out my notes. All right. So is everybody good with that? It's literally just plug and chug, right? I know my VI, I know my VF, I know my time. Plug in your numbers. All right. And then finally, we got to find our starting position. So let's see. We ended at a position of negative 50. Oh, this is ugly. Say that again?
How we position the velocity? How are we doing position of the velocity? Look at that.
I'm not even graphing it. I'm just trying to find the missing stuff.
Oh.
Okay? So to find the initial position, you can either kind of logic through it, or you can use this idea. I know that displacement is final position minus initial position, right? So that means my displacement, my 108, has got to equal my final position, negative 50, minus my xi. And do some algebra, and you find out that your initial position was negative 158.
I got 50.
Okay. So do I need to do the algebra on it?
I was just adding 50.
Yeah. Okay, so if you add 50 to both sides, that's fine. You get 158 equals not xi, but negative xi, right? So then you got to either multiply or divide by negative 1, and you get... So you end up getting xi equals negative 158 meters. All right, everybody good there? All right, so our position graph is going to be ugly because all of these positions are negatives. I think, honestly, when I wrote this, I probably wanted to make that positive 50, and I goofed up. Okay, so anyway, let's do this. So, what did I tell you yesterday? Which graph did we do first? Do the velocity graph first, right? So let's see, my velocity needs to include everything between 6 and 30, right? So here's 0, and I need to get up to 30. So what should I number by? I got 5 boxes. I can just number by 6s, right? So 6, 12, 18, 24, 30. All right, and then we need 6 seconds, and I've got 10 boxes, so I might as well just number by 1, right? So we'll just go 1, 2, 3, 4, 5, 6, and then we don't care about anything after that. So let's see, our velocity started at 30, and after 6 seconds, the velocity was 6. There's your graph. Good. Okay, now the position time graph. Excuse me. All right, I'm going to be a little sloppy here. This bold line suggests that that should be 0, but all of my positions are negative, so it kind of doesn't make sense to just try to squeeze everything between 0 and negative 158 into the bottom half of this graph, right? So I'm going to kind of cheat. Let's call the top of this thing a position of 0. Is that okay? So here's sort of my time axis now. And I'll just make sure that I write the problems better so that doesn't happen. So I need to get from 0 all the way down to negative 158. So what do you want to number by? I got 10 boxes to get down to 158. 20s works. You could do 16 if you really wanted to, and you'd end up at negative 160. But let's just go by 20s. So we'll call this negative 40. Notice I skipped a box. Negative 80, negative 120, negative 160, and negative 200 for my positions. Cool? All right, so I know that my starting position is negative 158, so that's going to be down here by 160, right? And I know that after 1, 2, 3, 4, 5, 6 seconds, my position should be negative 50, which is going to be right here between 40 and 60. Good? And then I need to draw it. So again, I asked the same question yesterday. Can I just connect the dot to the straight line? No, because the velocity is not constant, right? So there are two ways I can draw it. I can either draw it like this green dude. Oop, that's not at all. Well, I guess it's fine. Or I can draw it like this blue dude. Which one is right, green or blue? Hearing some votes for green. Why would it be the green one? Say it again. What's moving closer to zero? You're right, but I just want.
If you're accelerating, right?
So remember, you guys, how do I want to say this? The position time graph represents how fast you're going by the steepness, right? Okay. So in this problem, are we speeding up or slowing down? Slowing down, right? We're going from 30 meters a second to 6 meters a second. So we're slowing down, right? So that means my graph needs to start out steep, 30 meters a second, and then get less steep, 6 meters a second. So which one of these starts out steep and gets less steep? The green one, right? So the green one is the one we want because it starts out steep and ends up not steep. Okay? So Alex, you said it's getting closer to zero. The velocity is getting closer to zero, which means the slope has to get closer to zero. Does that make sense? And you're right, the position is getting closer to zero, but that isn't really important here. Because even if this had all been up sort of with a positive position, the graph still would have been shaped the same way. Does that make sense?
Yeah, no, I agree.
Is everybody good with that? All right. There's a lot of information contained in these graphs, you guys, so you really got to take it slow. So when you're drawing your position time graph, the question should be, is the thing speeding up or slowing down? Okay. If it's slowing down, it starts out steep and gets less steep. If it had been speeding up, then it would start out less steep and get more steep, like the blue one. Okay? So the green one is the right answer, the blue one is not. Good? Questions? All right. Let's do one last one. So this one is kind of the same idea, but we got a couple extra steps here because something special happens while the ball is rolling. All right, so this is similar to what you guys just did in the lab. All right, it says Roy rolls a ball up a ramp at 12 meters a second. The ball isn't going fast enough to get to the top, so it slows down, stops, and then rolls partway back down, reaching a velocity of -9 meters a second before Roy grabs it again, 7 seconds after he first rolled it. If the bottom of the ramp is a position of -10 meters, make a position time graph and a velocity time graph. And then it gives another tip. If the velocity hits 0, find the time when this happens. All right, so we're going to kind of have to do two sets of calculations here. But that might not be obvious yet. All right, so let's start by just taking apart the information in the example, just like we did in the first two examples. All right, so here we go. Roy rolls a ball up a ramp at 12 meters a second. So what do you guys got? That's the initial velocity, right? That's how fast it's going when he first rolls it up the ramp. It's not going fast enough, and eventually it reaches a velocity of -9 meters a second, right? So that's my final velocity, right? What's the significance of the fact that it's negative, you guys? Like, what does it mean that the velocity is negative? What do you got, Jeff?
It means that we're going backwards.
Yeah, it's coming back down the hill now, right? It started going forwards, which is up the hill, and then later on it goes backwards, which is back down the hill. Everybody good? That's your t-shirt, Jack. That's nothing here. All right, and then the time is 7 seconds, right? All right. I'm trying to get in the habit of writing SEC for seconds. Otherwise, sometimes the S looks like a 5. So, all right. It says if the bottom of the ramp is a position of -10 meters. So, how is that pertinent here? Like, what does that have to do with this problem? Good. That's the initial position, right? That's where the cart started at the bottom of the ramp. So that's my initial position, right? Okay, so we got to find some missing stuff, yeah? So what do we need to find? Yeah, we got to find our acceleration. So let's see. Acceleration is Vf minus Vi all over t, right? So you're going to get negative 9 minus 12 is negative 21. Divided by 7, you're going to end up getting negative 3 meters a second squared. Cool. All right, we got to find our displacement. So we'll stick with the screwdriver. If it ain't broke. Oh, that's not right at all. So let's see. My Vf plus Vi is going to give me 3. Half of that's going to give me 1.5. Times 7 gives me 10.5 meters. Holy moly. And then my final position I can find by rearranging the tweezers, right? It's just displacement plus initial position if you rearrange that. And you end up getting 0.5 meters. All right. Problems, you guys? So let's start graphing this thing and see if we can figure out what's going on. Where should I start with my graphs? Velocity, right? Okay, so there's my little scrolly bar. Yeah, we're fine. Okay, so let's see, velocity. The velocity has to include everything between 12 and negative 9. So here's 0. I got to get up to 12. I got 5 boxes to do it in. What should I number by? Yeah, let's number by 3s, which actually is convenient because that's our acceleration. So here we go. We're going to go 3, 6, 9, 12. And then going the other way, we're going to get negative 3, negative 6, negative 9. And after that, I don't care. And we've got 7 seconds, 10 boxes, so we'll just number by 1s. So 1, 2, 3, 4, 5, 6, and 7. And I know that my velocity started at 12, and after 7 seconds, the velocity was negative 9. Connect the dots. We'll give everybody a minute to catch up with their drawings. All right. Everybody good? Any questions before I go on? This is about as hard as they get, you guys. If you can do this, you're in pretty good shape. All right. Everybody good? All right. So now we got to make our position time graph. So let's start by doing the same thing that we've been doing before. Oh, we sort of can't, actually. All right. Let's hypothetically pretend that I had numbered my position axis. Okay, don't do this. Just listen for a minute. All right. So what I'm drawing in green, don't draw. All right. So my position starts out at negative 10, and then it ends up at positive 0.5. So suppose I did this. Suppose I went negative 2, negative 4, negative 6, negative 8, negative 10, and then 2. So my position at time 0 is negative 10. And then after 7 seconds, 1, 2, 3, 4, 5, 6, 7, my position is 0.5, which is going to be right here, right? Cool. So then you try to connect the dots. I can't do it as a straight line because the velocity is not constant, right? But here's the issue. There's something important happening here that hasn't happened on any of the graphs we've done so far. It changes direction. All right? So remember, you guys, on a position time graph, how do you represent direction? Like if you're moving forward, show me your hands. What does the graph look like? Slopes uphill, right? And if you're moving backwards, it slopes downhill, right? So what's going to happen is my graph, sometimes we're moving forwards, sometimes we're moving backwards. So my graph's going to have an uphill portion and a downhill portion, right? So my graph's going to look something like this, but I don't know exactly what it's going to look like because I don't know where this point happens or what the displacement is there. Does that make sense? So everything I drew in green here is garbage until I figure out how far it goes to this point where it stops and turns around. Follow? Question?
Why is the final just
How did I get that, you mean? Did I do my math wrong? No. I think I'm good, but let's double check. So, if you didn't hear, the question was, why is the final position 0.5? So, I'll do that in blue. So, let's see. We know that our starting position is negative 10, right? So, on a number line, here's 0, 1, 2, 3, 4, 5, and then negative 10, right? Cool. And my displacement is 10.5. The fact that it's positive 10.5 means, what does that mean? Tell me what you just realized. That you're going to go 10.5 in a positive direction, right? So if I start at negative 10 and then go this way 10.5, you're going to get just past 0 by 0.5, right? Algebraically, it's this. Displacement is final position minus initial position. So our displacement is 10.5. Final position is what we're looking for. Initial position is negative 10. The minus negative actually becomes plus, right? And then to solve it, you subtract 10. Cool? Cool. Thank you for asking when you were confused. We need to be doing that. All right, so our final position is, in fact, 0.5 meters. All right, everybody cool? All right, so now we got to deal with this fact that there's a change in direction. So on my velocity time graph, where does the change in direction happen? I'm going to repeat the question, and then Liam just gave me an answer. The question was, on the velocity time graph, when does the direction change? I think is what I asked. All right, and you said 4 seconds, Liam?
Yeah.
How do you know that?
It's crossing at 0 and it's starting to get further away from 0.
Good. That's when the velocity is 0, right? Look, before 4 seconds, my velocity is positive, right? That means it's going uphill. After 4 seconds, the velocity is negative. That means it's going downhill. So this point right here, 4 seconds, is the important point. That tells me when we're turning around, right? All right, now sometimes your graph won't tell you that explicitly. Like, I picked nice numbers here so that this sort of worked out and hit right at 4 seconds. If it didn't, we could figure it out, couldn't we? Here's what we would do. We would say, let me do this. Insert blank page. All right, so here's what we would do. We would say, all right, well, I knew that my initial velocity was 12 meters a second. I know my acceleration is negative 3 meters a second squared. I want to find out at what time will it stop moving forward. Does that make sense, you guys? So then pull out your x, right? And solve it. So let's see, you're going to get 0 minus 12 over negative 3, divide it out, and you get, 4 seconds, exactly what the graph showed us. All right, but if you're not sure, if you draw your graph and you're like, is that really crossing there? This is a good way to check. Make your VF 0 and solve for your time. Cool? All right. So now what I need to do is I need to figure out what the position is at the end of those 4 seconds, right? So that I can do my position map over here, my position graph. Okay? So let's do that. Let's find the displacement during those 4 seconds. Again, you can use any of your 4 equations. You guys seem to like the screwdriver, so here we go. 1/2 VF plus VI times T. So I'll actually plug in the numbers here. So when it stops, my final velocity is 0. My starting velocity was 12. The time it takes to get there is 4 seconds. So half of 12 is 6, times 4 is 24 meters. And since my initial position was -10, that means my final position is going to be what, you guys? Excuse me. What do you got? If we start at a position of -10 and then roll forwards 24 meters before we stop, where are we going to stop? 14, right? -10 plus 24, right? And so you get 14 meters, right? Cool? All right, so that was what we needed for our graph. So let's go back. So now what I know is at the bottom of the ramp, my position is -10. And even though it rolls back to a position of 0.5 meters, there's a point in the middle there where it gets to a position of 14. And that occurs after 4 seconds. So my position axis has to go from -10 all the way up to 14. So what should I number by? Yeah, let's go by 3s, right? So 0, let's see, is that going to work? 3, 6, 9, 12, aha, 15, we made it. Because we needed to get up to 14, right? And then going down, we got to go -3, -6, -9, -12, and that's far enough. And then my time is 1, 2, 3, 4, 5, 6, 7. And so now I have 3 points to plot. Okay? I've got that my starting position was -10. I've got that my ending position is 0.5. And I also know that at the top of the path, when it stops, 4 seconds have passed, and the position is 14, right? Make sense or no?
Where did you get the 4 seconds?
That was because that's when the velocity is 0. Right? That's where did I get the 4 seconds was the question. If you missed it, that was 4 seconds to get to a velocity of 0. Follow or no?
How do you think that's the velocity?
What, so the question is, why do we want the velocity to be 0? Why? Why is that point so important, you guys? It's always going to be important. That's when it stops moving forwards and comes back. You see that or no? No? Not so much?
I wasn't really paying attention, so I was just like my fault.
Okay, but it's important enough that we should spend a minute on it, because if you're confused, then somebody else is too. All right, so check it out. Here was the deal. So our cart started at a position of -10, right? Oops. And it rolled up the hill and it came back down, and he stopped it after 9 seconds right here at a position of 0.5 meters, right? In order to graph this, we need to know what this position is. Cool? And so what I did was I said, okay, well at this point my velocity is 0. I need to find out how much time it takes to get there. All right? And so I made my VF 0 and I did some algebra to find the time. Cool? Everybody good? Cool. Thank you. I appreciate the honesty, but we got to get it. Okay, cool. So now what I know is after 4 seconds, my position is 14. So now we're good, right? We can just connect the dots, right? Do I use 2 straight lines? Straight up, straight down? No. It's going to be a nice parabola, right? So it should hopefully look something like that-ish. Do the best you can. And if you do it right, this dot should be at the top of your parabola, right? Because that's the highest it gets. Cool, you guys? That took longer than I thought it would, but you gotta know how to do that. So, any questions? All right, finally, I'll wait till everybody's done drawing. All right, so finally, the acceleration time graphs. The acceleration time graphs are going to be easy. Because in every problem we did, the acceleration is constant, right? So in that last problem, what was the acceleration, you guys? negative 3 meters a second squared for 7 seconds, right? So here's your acceleration time graph, which you do have to draw on the homework. Acceleration measured in meters per second squared. Time measured in seconds. I need 7 seconds. 1, 2, 3, 4, 5, 6, 7. And my acceleration is negative 3. 1, 2, 3. So here's the graph. That's supposed to be a horizontal line. Right? The acceleration is always negative 3. So just draw a horizontal line at whatever your acceleration is. Okay? So the idea is, in this class, for any given chunk of your graph, the acceleration is always going to be constant. Cool? All right, a couple quick announcements before I set you free to get started on the homework. Where did my announcements go? Oh, nuts. I wrote them in yesterday, and they didn't get added in here. All right, let me see if I can remember what they were. Couple quick things. Thing 1. If the problem doesn't say otherwise, you can assume that your initial position is 0 when you're doing the problems. If the problem does not say otherwise, assume your initial position is 0. Oh, here was the big thing. I remember this. All right. On problems 5 and 6, it says a car accelerates forward. Well, here. Let's do this. Just graph a total of 5 seconds. All right, there's 2 parts to the graph. There's 3 seconds where he's accelerating, and then it says then he goes at a constant speed. So just have that be 2 seconds. So you get 3 plus 2 is 5 seconds. Cool? This problem is going to be tricky for you guys. We did not do it exactly like this in the notes, but I want you guys to try it. So do the best you can with it. And if you struggle, don't stress. Okay? We'll go over it for sure. I think that is all that I needed to say about that. There's not room on the sheet to do your work. So please do it on a separate sheet. Cool. So there's 8 of these little graphs. The first ones are super easy, and then they get progressively more difficult. I shouldn't say they're easy, but they're more straightforward. None of these are easy. But all right, are we good? All right. We had 10 minutes. I'm sorry it's not more time. I really hoped it was going to be.